Relative velocity. First question, how will I know that this is a question that's dealing with relative velocity? Because there will be two objects in the question. It's really asking what happens when there's more than one object, and we don't want to try graphing it. I used to do a big graphing section, but we want to analyze the speeds, but there's more than one object. As an example, you're driving down the freeway with your speedometer reading 100 kilometers per hour. When a Ferrari hurtles past you, its speedometer reads 180 kilometers per hour. Supposing a tow truck was parked at rest beside the freeway, what would the tow truck see? Okay, so I'm going to zoom in a little bit here. So the velocity of u relative to the tow truck, how fast is the tow truck going right now if it's parked on the side of the road? 0. How fast are you going according to this question? So I'm going to argue, or what would the tow truck see you doing? Don't overcomplicate this. How fast are you going relative to the tow truck? Maddie? Yes. I changed this from an Escort to a Ferrari, and I've realized I forgot to change the subscripts. So it says Escort relative to the tow truck. That's Ferrari relative to the tow truck. How fast is the Ferrari going relative to the tow truck? 180. We're going to keep our speeds in kilometers per hour for now. Now, here's where we get tricky. Now you got to use your imagination. What would you see? How fast is the Ferrari, not the Escort, how fast is the Ferrari going relative to you? And I'm going to tell you the answer is not 180. How fast do you perceive it going? Maddie? Why? Okay, and here's where Einstein stepped in. He said, because as far as you're concerned, you are at rest and the world is moving around you. Everything is relative. Relative to, this is why he called it relativity. So relative to you, you would see the Escort traveling at 80 kilometers per hour. With me so far? How fast is the tow truck traveling relative to you? Let's say it's in front of you, and you can see its back lights. You see its back lights coming towards you, coming towards you, coming towards you, coming towards you. Zoom, you go past it. Now it's behind you. You see its front lights going away, going away, going away, going away. Ethan, what do you think? No. Yeah. Negative 100. As far as you're concerned, it looks to you. Now you got to use your imagination. If you are at rest, it looks like the tow truck is in reverse coming towards you because you see its back lights coming towards you, and zoom as you go past it, or as it goes past you. It's all relative. Then you see its headlights retreating in the distance, Justin. Relative to you, that tow truck is traveling backwards. Because you see its rear lights coming towards you, and then once you're past it, once it's past you, you see its headlights retreating away from you. Which answer is correct? Yes. Einstein said there's no way to prove any of those answers is wrong. What would the, Ferrari, I got to fix this clearly, see? What would the Ferrari see? Okay, what's the velocity of u relative to the Ferrari? Well, the Ferrari, when it's behind you, sees your backlights getting closer and closer and closer and closer, and then zoom, and then the Ferrari, when it's in front of you, sees your front lights going further and further back in its rear view mirror. As far as the Ferrari is concerned, what's the difference in speed? Yes? But does the Ferrari see you traveling forwards or backwards? Yeah, because when you're in front, it sees your back lights getting closer. That's the same as if you're at rest and you're backing up. So I wrote, by the way, why. You don't need to do a long explanation if you don't want to, but we're trying to describe why. This is where you really have to, Chantel, use your Sesame Street imagination here. And what about the tow truck relative to the Ferrari? As far as the Ferrari is concerned, the tow truck is traveling at negative 180 kilometers per hour. Why? Because when the tow truck is in front, the Ferrari sees the back lights coming towards it, right? And when the tow truck is behind, the Ferrari sees the headlights retreating that way. That's just the same mathematically as though the tow truck was in reverse and the Ferrari was parked. No difference. Did I say reverse? Negative. We okay on that end? That's some deep thinking here. Okay. Mr. Dewick, I wrote, is there a short way to write this? Yep. I would write, instead of escort Ferrari relative to you, you could write velocity of Ferrari relative to you. We use an arrow pointing as an abbreviation for the phrase relative to. So the velocity of you relative to the tow truck. I'll use a T for tow truck. I'll use an F for Ferrari. I'll fix the typo so that it no longer says escort. Originally, when I made this up, for some reason, I used a escort, and then I went, wait a minute, that's a weak vehicle. They don't go very fast. Change it. So, you don't perceive the Ferrari to be moving away at 180 kilometers per hour, but at 80 kilometers per hour, because you're also moving in the same direction. So the relative velocity of any moving object depends on your point of view, fancy word, frame of reference, or reference frame. Sure, you see, for example, the Ferrari moving away from you at positive 80 kilometers per hour because once it passes you, you see its backlights getting smaller and smaller and smaller, and that's how things behave if you're at rest and they're pulling forwards. But as far as the Ferrari is concerned, it's at rest, and it sees you getting further and further and further behind it, going in reverse. Both are right. Both are equally valid. There is no way to prove that one person is wrong and one person is right. You may have experienced this if you've ever walked on a moving walkway while you're in an airport. Because you look at the people that are walking beside you on the ground, and they seem to be walking really slowly. No, you're probably walking at the same speed, but you have a relative velocity. Okay. So here's our first thought experiment. It says, what is the velocity of the train passenger relative to the observer on the ground in each case? So we're going to say, what is the velocity of the passenger relative to the observer in each case? First of all, how fast is the passenger walking in the first example? Let me zoom in so you can see. How fast is the passenger walking? Yeah, 1.2 meters per second. How fast is the train going? 15. Now, as far as the passenger is concerned, then, he is walking at 1.2 meters per second. How fast does he appear to be walking relative to that observer who's watching from the Earth? Hannah? Yeah. Alan, you're not on your phone right now or anything foolish, are you? That would be silly. Put it away. What is the velocity of the passenger relative to the observer? And I'm saying velocity, did I use a vector sign? Because clearly here, direction does matter. Yes? Okay. What's the velocity of the passenger relative to the observer here? Yeah, Mackenzie. 13.8. Yeah, 13.8. Right? 15 minus 1.2. Don't forget to carry the 1. Yeah, 13.8. Mackenzie, Does that mean that if this passenger could run at 15 meters per second and ran in the opposite direction that the train was moving, what would the observer see? As far as they were concerned, the passenger would be standing still because the velocities would be canceling out. Yeah? I wonder. Oh, did I go kilometers per hour? Meters per second. Thank you. Who pointed that out? Chantal, was that you? Or the Aisha? Candy for you. I'll get you one in a second. Make sure I don't forget. Oh, and I owe a candy to whoever won the... Was Louisa? Okay, make sure I don't forget. Oh, that whole table gets candies. Okay. Example 2. A zebra is running away at 50 kilometers per hour from a cheetah going at 90 kilometers per hour. So the zebra is in front. The cheetah is behind. What velocity does the zebra see the cheetah having, and vice versa? Okay, so what is the velocity of the cheetah relative to the zebra? First of all, what's the difference in speed here? Hannah? 40. Now let's imagine we're the zebra, and let's imagine the zebra has a rear view mirror. I know that breaks the... but let's pretend it does. What does it see? It sees the front, the head, the front part of the cheetah getting closer and closer and closer and closer. It sees the cheetah running forwards. So we're going to say it sees the cheetah going at positive 40 kilometers per hour. What about from the cheetah's point of view? So what's the velocity of the zebra relative to the cheetah? Well, what does the cheetah see? It sees the hindquarters of the zebra getting closer and closer, which really, Morgan, I'm going to argue mathematically is the same as if the cheetah was stopped and the zebra was walking backwards towards it. It's exactly the same phenomenon. I see the hindquarters getting closer. So there's a difference in speed of how big? But for the cheetah, it sees the zebra traveling at... Okay. Now let's start to apply this and do some physics. So, Justin, if there are two objects, the rule is going to be we're going to use the relative speed, the relative velocity. But I got to be honest, very, very rarely will you need to worry about negative or positive. So I've talked about negative and positive just to help you kind of imagine what the relative velocities would be. But C says this: if the zebra starts out 90 meters ahead, how long will it take until the cheetah catches up? What's this question asking me to find? Let's do our old approach. T equals question mark. And I've told you for all of these, A is 0. What if I wanted acceleration? Get your PhD in general relativity, but you're in for some ugly math. I think it ends up being 10 dimensions, and you have to do 4-dimensional tensor fields, I think. The big Einstein had the idea of general relativity in 1904. It took him, Albert Einstein, 10 years to learn and derive the mathematics. If it took him 10 years, I'm willing to just say, okay. What else do we know? What's that 90? Okay. Mr. Dewick, is that D, is that 90 negative or positive? It's all relative. And I'm just going to say, for all of these, I just assume I'm going to focus on the positive values. So we do have a relative speed. So I'd like you to write V and then put a little REL as a subscript. What's the relative speed between, and I'm not saying velocity anymore, what's the relative speed between the cheetah and the zebra? What's the difference in speed, Morgan? You told me this earlier. 40. I don't care about the positive or negative. I'm looking for an equation that has a T, an A, a D, and a V in it. There is one. It's going to be D equals VIT plus a half AT squared. Write that down just this once. But Emily, what did we just say A was? Which means this whole thing is going to vanish. And here's what else it means. If you're not accelerating, that initial velocity is your final velocity, is your middle velocity, is your at all times velocity, because you're not accelerating, which means your speed isn't changing. So really, you can think about this becoming d equals vt, where the v is that one. That's going to be the equation that we're using for this lesson. Is it a new equation? No, it's d equals vit plus a half at squared. A is 0. Okay, get rid of that term. And then let's clue in, if there is no acceleration, your initial and your final, and all of them are going to be the same. And if there's two objects, use relative. How do we get the t by itself? Because it wants us to find t. How do we get the t by itself? Yeah. So you're telling me the time here is going to be d divided by v rel. This would make a good multiple choice question, and you better believe one of the answers would use the 80 kilometers per hour. One of the answers would use anyways. What's the distance? 90 over. Problem. 90 what? What are the units? Meters. 40 what? What are the units? So up here, I'm going to write kilometers per hour, and let's convert that to meters per second. Is it times by 3.6 or divided by 3.6? I can't remember. Oh, we put it on our sheet. What is it? 40 divided by 3.6? Is what? Do this on your calculator, please, Brady. I'll show you why. You get 11.1? No. Do you get 11.11? No. You get 11.1111111111 repeating? Okay. So I'm going to write 11.1 meters per second, but I'm going to tell you, Brady, this is why I said type it into your calculator. When I calculate this, don't write this down. I'm going to put my answer button right there, because that way I'm not introducing error. When we go through the test in a few days, you're going to see a lot of you, a number of people lost a half mark either for bad rounding off or because they rounded off one of their answers and then used that to find the next answer rather than just store that on your calculator and use your answer button. You don't use a rounded off answer to find another rounded off answer, because now that one's off by even more, and then don't use that to find something else. I'm going to write 11.1. But I'm going to type 90 divided by answer button. How many seconds? If shelter is 8.2 seconds away, dead zebra. If shelter, Eli, you with me? Yeah, not looking at your phone or anything, are you? No? Okay. So, really, a more interesting version of this would be, and this is how evolution has evolved, that's a circular reasoning. Cheetahs can only sprint for about 8 or 10 seconds at a time. So the zebras actually do this math in their heads, and they realize how far away they need to be, because they can sprint for longer, just not as fast. So that if the cheetah starts to run, this zebra starts to run, and the zebra can outlast the cheetah. Those zebras that are bad at math get eaten. Survival of the fittest. Those cheetahs that are good at this don't get eaten. So those zebras that are good at this don't get eaten. But this really is what much of nature comes down to, those 0.1s of a second. Example 3, Nick and Cole are having an argument at an airport on a windy day. Nick says that airplanes should take off with the wind. This way the wind pushes them from behind so that planes can travel faster on the runway. Cole says that airplanes should take off into the wind. He's not sure why, but it makes sense to him. Who is correct? If you're at an airport, do you want to take off with the wind at your back, or do you want to take off with the wind in your face? Put your pencils down, look up. Sorry? Cool. So the video that we just watched, what was the speed of the plane relative to the ground? 0 meters per second. What was the speed of the plane relative to the wind? Takeoff. All right. State the relative speed in each case. We don't care about negative or positive, just the relative speed in each case. So we're going to start off with these first two trains that are each going 40 kilometers per hour. What's their speed relative to each other? This is meant to be really obvious. Don't overcomplicate it. 0. What about this one here, where they're both going in the same direction? What's their relative speed? You're right, 20. One would consider it negative, one would consider it positive. It depends on which one we're looking. I don't care, I just know the difference is 20. What's the relative speed of these two? Give you a hint. 60. Ethan, what would be a worse car accident? Getting rear-ended or a head-on collision? There. And the reason is, if you're in opposite directions, your relative velocities are going to combine. If you're in the same direction, your relative speed is going to be the difference, but not the adding. Let's do a couple more applications here. I like example 5, I like example 5, I like example 5. Example 5 is a nice question. Example 5 says, how long does it take these trains to completely pass each other? First of all, I have to define what I mean by completely pass. Aisha, to completely pass, the back part of this train has to get past the front part of the bottom train. Maddie, what's this question asking me to find when it says how long? I wrote here, since both trains are moving, this seems like a difficult task. No, both trains are not moving, not in our relative speed or relative velocity world. We are going to say that A is 0. What's the relative speed of these two trains? What's the speed of these two trains relative to each other? 8. And how far does the back train have to travel? How far does the top train's back have to travel to get all the way past? You guys with me? We're back now? Yeah. How far does the back of the top train have to travel to get past the front of the bottom train? Yeah, 250. Mr. Dewick, are you saying this is the zebra question in disguise? Well, it's not much of a disguise. Is there more than one object moving? This is a job for relative speed. Are there two objects? This is a job for relative speed. In fact, we can again say D equals VT plus a half AT squared. What's A? 0. Why no VI? Because there's no acceleration. In fact, this V here is going to be relative speed. We can again say to get the T by itself, it's going to be D divided by V. So it's going to be 250 divided by 8, which is what?
31.25.
I'll go to 3 sig figs because it looks like 13.0, 5.00, 150, decimal, and 100. It looks like everything is 3 sig figs in the picture. But yeah, I'd take 31.25. What if instead of heading in the same direction, what if they were heading towards each other? What would the relative speed be? 18. What if they're heading away from each other? What would the relative speed be? Still 18. If they're heading in the same direction, bigger minus smaller. If they're heading in opposite directions, add them up. This last one? Oh no, we got Hot Pursuit and cool videos. Okay, almost done. As you hurry to catch your flight at Vancouver Airport, you encounter a moving walkway. You've seen them. That is 85 meters long and has a speed of 2.2 meters per second relative to the ground. If it takes you 68 seconds to cover 85 meters when walking on the ground, part 1, what does part 1 want me to find? Justin, what does part 1 want me to find? Don't overcomplicate it. Looking for begins letter S, ends in the letter D. Yeah. What's our symbol for speed? V, because just, right? V, velocity with a vector sign, speed. Let's do that. Justin, what's that 68? What's that 85? Yep. Is there a walkway moving? Say yes. Is there a person moving? Say yes. Are there two objects moving? This is a job for relative velocity or relative speed. A is going to be 0. In fact, Justin, again, I think we're going to end up with D equals VT. How would I get the V by itself, my friend? Divide by what? So you ready? What's going to drop down like a domino? The D. And then I want to get the V by itself. So what will I move over? Yeah, divide by T. Okay. So my walking speed is 85 divided by 68. (1.25 meters per second). If you want to put this in context, remember the picture of the passenger on the train with the little backpack that I showed you earlier? This is the passenger's walking speed in the train. This is my walking speed on the ground. All right. Now, I walk on the walkway. How long will it take me to cover the 85 meters? Aisha, what's this question asking me to find? Now, D is still 85. A is still 0. But now, since I'm on the moving walkway, there are definitely two speeds involved here. I'm going to use my relative speed. What's my relative speed? How will I figure it out? What was the speed of the walkway? It's up there somewhere. Yeah, and? What am I going to do with those two numbers? I'm going to add them because I'm going to be walking faster relative to the ground. And I won't round this off at all. I can do this in my head. Do you get 3.45? Double check me. That's my speed relative to the ground, and this 85 meters is relative to the ground. So now I can go D equals VT. T equals D over V. So normally it takes me 68 seconds to walk this. How long does it take me now with the moving walkway? $24.6. We've cut my time over in half, and if you don't think airports view that as money, this is why they build those walkways. Lets them bring in more flights. It lets you start out further out. Lets you build terminals further out, and you can still get everybody to make their connecting flight. Now, of course, if you go to YVR, it's not just one moving walkway. They'll have a bunch in a row. But I'm telling you, they've run the numbers like this. This is how they can figure out how much time you need to get to your next gate for a connecting flight. Of course, none of you have done Part B. None of you have gone on one of those moving walkways and decided to turn around and start walking in the opposite direction of the walkway. I see Brady sheepishly laughing here. Colby is looking around to make sure no one else is noticing that he's... All of us have tried this at least once if it's not crowded and we're not being a meathead. Right? Okay, so if once you get on the walkway, you immediately turn around and you start walking in the opposite direction, what's your new speed relative to the ground here? So walkway was 2.2. You're walking at 1.25. What's the speed on the ground here? How will I calculate that? I think subtract this time. Now, this is not where we have really... I fibbed a bit because in the previous question with the trains, I said, look, if you're in the same direction, you add them up. And if you're in opposite directions, so I said if you're in the same direction, you subtract. And if you're in opposite directions, you add them up. Here we're doing the opposite. I can't give you a hard, fast rule. All I can say is, Hannah, draw a little picture like I did, kind of think about it, and it's usually pretty intuitive. So here, do you get 0.95? Double check me. Is that right? Yes? Meters per second? So if I go backwards, how long would it take me to walk this way? Nope. Are you spotting that it's d equals vt over and over and over and over? Okay, because a is 0. So t is going to be d over v. What's the distance? Still 85. What's my new relative speed now? 0.95. And I get 89.5 seconds. Does that make sense? What did it take me to, how long did it take me to walk this just at my normal speed? Was it 68 seconds or something like that? Okay. So walking backwards, yeah, it should take me longer. I knew the answer was going to be bigger than 68. Yeah, it makes sense to me. One more, we're done. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. The police are in hot pursuit of a car which is 320 meters ahead. It's going 150 kilometers per hour. I already see meters and kilometers per hour. We're going to have to do a conversion here. Spot that already, Chantel? If the police are going to ram the car in 20 seconds, how fast do they need to be going? Chantel, when you're done yawning, is there a police car in this question? Are there bad guys also in this question? Is there more than one object in this question? That's a job for relative velocity. In fact, what this question wants me to find is that. And we're going to do that by using this and getting the v by itself. So, did they give me a d? Gagan, did they give me a d? What? 320 what? Units? Okay, so now I'm committed to meters. Did they give me a t? That's a time? Oh no. Ah. So this will give me an answer in meters per second, I think, if I get the v by itself. V is going to be d over t. Is that okay, Gagan? Yes? It's going to be 320 divided by 20. I can do that in my head. Double check me. Is it 16? 16 units. This is meters per second. I don't want an answer in meters per second. I want an answer in kilometers per hour. So let's take this VREL, relative speed, which is 16. How do I go back to kilometers per hour? It's something to do with the 3.6. Is it divide or times? Times? Which is what? 57.6? And that's kilometers per hour. But that's the relative speed. How fast are the bad guys going? 150? So how fast do the police have to be going? Yep. 200. And you know what? We need to add that 57.6 to the bad guy's speed. Yes? The police is going to be 57.6 plus 150. Oh, I can do that in my head. It's 207.6. I should have done that in my head, yeah? And that's kilometers per hour. Any slower, they won't catch them in 20 seconds. Any faster, they'll catch up to them sooner. Fair enough, but they got to be going at least that fast. I got a couple of cool videos to show you, but first I'll give you the homework if you want to start. What's your homework? I like number 1. I like number 2. 3 is good. 4 is good. 5 is good. 6 is good. 7 is good. I'm going to assign most of these, so right now I've assigned everything. Number 7, are the trains heading towards each other in number 7? So what's their relative speed? It's not 4. What's the relative speed here? 16, because head-on collisions are worse than rear-end collisions. Okay? 7 is good. 8 is good. 9 is good. 10 is good. Yeah, 11 is good. Mr. Duck! Sorry. 12 is good. I'm assigning all of them. You're not going to have any homework next class, so don't freak out. A couple of videos to show you. Put your pencils down and look up.